Hello everyone, I'll be doing problem 4 from Controls Homework. For this problem, we are given a block diagram for which we need to condense it and find the steady state error for the system. To do this, we are given inputs. We have step, ramp, and parabola for our inputs. And to condense the system, what I am going to use, I'm going to use the flow diagram Mason's rule method to do this. So to do this, simply have a straight line. This is going to represent your forward path. And in your forward path, you're going to mark these points like V1, V2, wherever you see something branches out and connects to another point. For instance, I have V1, which is going to be this point right here where you see this green line going and connecting at this particular point. And then I have V2, which is this point, V3, and C of S. So what you do, for instance, right here, after V2, you see you have 1 over S. So you would mark 1 over S for that part of the forward path. And all the blocks that are labeled as you see in the system, you would just mark them. As for the loops, what you would do is you look at the point where they start from. For instance, this 3 at 4s and 1 starts at C of S. So you would go at C of S and go to those particular points where these loops end at. So by the time you have everything that you have on the system labeled in your flow diagram Mason rules system, like you see here, now you can start writing some equations for them to find your Mason's rule. So we can have this. So we can have a condensed equation that we can get out of the system instead of solving for the system. You can do it that way, but I think this is a very systematic method, so there's very less chance of making a mistake doing this way. First, you write your forward path, which is going to be 1, which is right here, times 1 of S, times 2 over S plus 3. Your second forward path is going to be 1, and as you see this line going over, so you're going to have 1 again, and then 2 over S plus 3. So that's going to be your second forward path. Now we don't have anything else going around on the in the direction of C of S, so we don't have any more forward paths. Now let's label our individual loops, and to do that, let me what's this? Okay, so for our individual loops, you're gonna have 2 loops, and I'll explain you why. For the first loop, you're gonna have this big one. Now, for the loop, you gotta think of it in this way, that when you start from one point, it should make like a circle. I know it's not a complete circle, but think about that the point you're starting at, that it kind of makes like a U-turn, or it comes back to the same point, and that's going to be your loop. So if you look here, it's basically your forward path that you already had. So it's going to be 1 over S times 2 over S plus 3. And at C of S, we're going to take this bigger loop, which is -1, and it comes back to our input point, which is R of S. So that's going to be, you can say that as your first loop. Now for the second loop, we're going to have 1 over S, and then you have 2 times S plus 3, and it goes to 4S. So as you see right here, it goes back to 4S. Now, third loop, as you may be thinking, like, well, why aren't we using this? Well, the reason you can't use this is because of this loop right here, which is a forward path loop, and if you see that it contradicts the rule that we learned doing Mason's rule, which means that we cannot have this as an individual loop. Once you do that, then you would have to know your non-touching loops. As you can see in this flowchart, all of your loops are touching the forward path. So that means we're not going to have a non-touching loop because all of them are touching the forward path. So our del 1, del 2 is going to be equal to 1. And once we have all this information, you can compute for delta, which is simply 1 minus the sum of the individual loops. Plus is going to be the product of your non-touching loops, but in this case we don't have any, so it's just 0. And then you do some algebra for this. So after some arithmetic, you would end up with, in the numerator, s plus 17, and in the denominator it's going to be s plus 3. Now you have delta, and we can find our condensed transfer function by using Mason's rule. So as you know that transfer function is the output over the input, and in Mason's rule it's defined to do that as 1 over delta, the sum of the forward path times your del 1, del 2 for your paths. So it's going to be P1, which is forward path 1 times delta 1, plus forward path 2 times delta 2 divided by the delta. And if you substitute the values that we found, you would come up with 2 times s plus 1 divided by s times s plus 17. Now, once you have this this form of this for this equation, now you would use the step input functions they gave us in the problem to find out for your steady state error. So first one is going to be our step, which is 15 times u of t. And if you look in your book, or if you have a table for your for these values, for the step, it's k divided by 1 plus the limit when s is approaching 0 for the transfer function. And for this part, you're going to have, for k, you're going to plug in your 15, and it's going to be 1 plus the equation that we just found out. And if you do that, since s is approaching 0, it's going to be infinity. And a number or a constant divided by infinity, we know is 0. So you may be thinking like, okay, well, I have this 1 here, so what about this one? Well, this term, which is infinity, is much greater than 1, so we actually neglect 1 and we consider infinity to be our dominant term. So 15 divided by infinity is equal to 0. Now for the next input, which is going to be ramp input, the formula given for that is k divided by limits when s is approaching 0 for the transfer function. And in this case, since it's a ramp function, as you know from your Laplace table properties, it's going to be 1 over s. So you have s in the denominator, and that would cancel out the s from this equation that we have here, and you're going to end up with a constant value. And then if you divide this, then you're going to get 127.5. For the parabola, you're going to have 2 times k in the numerator, and in the denominator you have limit when s approaches 0 times s squared of g of s. So if you solve this, you get 0 in the denominator, because when this s cancels out, you still have this s term laying in the numerator, in the denominator, which makes the denominator go to 0. And a constant divided by 0, you're gonna get infinity for that. So that's pretty much it to this problem. Thank you. I hope this problem helps you out.